Welcome to that of the PG students for the NET examination 2024. Now I am discussing regarding the next question solution 2024. First problem is the major product formed in the following reaction sequences. This is the chemoselective oxidations of the different type of alcohol. One is the allylic alcohol, another is the non-allylic alcohol. Here the allylic alcohol undergoes oxidation in presence of manganese dioxide to produces the aldehyde, and then this aldehyde group is protected by the 1,3-diol to form the cyclic acetyl intermediate, and then the 3-hydroxyl group is oxidized in presence of pyridinium chlorochromate to give the desired product. So the correct option for the given problem is the 2. Now we are going to that of the next problem regarding the ozonolysis reactions. In the ozonolysis reactions, two alkene group are cleaved to form that of the carbonyl compound. So the given problem is the ozonolysis of terpene gives equimolecular mixtures of acetone, alpha hydroxy, acetaldehyde and 4-oxopentenyl. These are the fragments of the ozonolysis product. If we rearrange in the proper way, then we get that of the particular product or that of the ozonolysis reactant. This is the ozonolysis reactant, and the option 4 is the correct option. Similarly, if we see that of the ozonolysis reactions on that of the partially reduced product of the cyclohexadiene derivatives, the ozonolysis produces the ester and the aldehyde groups, and after reduction chemoselectively aldehyde group is reduced. Here the ester group remain intact. The abnormal ozonolysis reaction also take place in case of the alpha-beta unsaturated ketones, where the alpha-beta unsaturated ketones undergo ozonolysis to form that of the ketone and the carboxylic acids derivatives. Now the problem is that of the correct set of reagent can affect the following conversion is. Here the different type of the reagent is given for this conversion. Here the less substituted alcohol group is formed. In presence of the metachloroparbenzoic acids, it first oxidized to form the epoxide derivatives in one side, and in presence of the sodium cyanoboroiodide, in presence of BF3 etherate, it cleaved the CO bond to that of the more substituted end, and the hydride ion is consequently attacked to give that of the desired product. And in presence of the osmium tetroxide NMO, the alkene is functionalized to give that of the cis-diol, and in presence of the THCl pyridine, it produces the epoxide derivatives which undergoes epoxidation take place. So the desired product is not formed. In the last case, the Mitsunobu inversion will take place and the desired product is not formed. So the correct option is the 1 option. Now the problem for that of the NMR spectroscopy coupling constant determination. If we consider the following compound where 3JAB and 3JBC represent 3-bond coupling between HA and HB and HB and HC protons respectively. In the first case, the 3JBC has greater coupling constant compared to that of the 3JAB. So the BC proton, that is the B and C proton, B proton is coupled by the CH3 proton to form a quadrate. Means this is the 4 lines is breakdowns, and after the 4 line, the HB is then coupled with that of the HA and produces doublet. So the quadrate of doublet is formed when in case of the 3JBC has greater coupling constant than that of the 3JAB. But if we see that of the 3JAB is equal to 3JBC, means the coupling constant is same, that is the CH3 and HCH3, that is C-type proton, is similar coupling with that of the HA proton. So the total number of proton is 4, and according to the n+1 rule, it gives that of the 5 lines. This is the quintet. Similarly, if we see that of the CH2, consider that of the JAB is equal to that of the JBC, then the 4 lines plus 1 means 5 lines are formed, and the intensity ratio can be calculated using the equation, and this is taken from that of the Pavia book that has been well explained in this book. The next problem is the reduction problem, where the sodium in liquid ammonia produces the partial reduced product. That is, the batch reduction will take place, and after the batch reduction, Wilkinson reduction catalyst is used for the reduction, and here the less hindered alkene is reduced compared to that of the more hindered alkene, and then the more hindered alkene hydroboration to give that of the corresponding alcohol. So the correct option is the 3. Similar problem was taken from that of the Carothas book, where the partial batch reduction followed by the quenching of the alkyl bromide and then isomerization we get that of the desired product. Similarly, here the Wilkinson catalyst can be reduced the less substituted alkene in presence of the more substituted alkene. Next problem is the correct intermediate formed in the following reaction. This is the examples where the carbene is formed in the intermediate in presence of the methyl trichloroethanoate. The trichloroform carbon anion is formed, which undergoes dechlorination to produces the carbene intermediate, and this carbene intermediate undergoes added to give the cyclopropane intermediate, which undergoes cleavage to give the desired product. So the correct intermediate for the given problem is the option 4. The tosylate that on solubilisis will give the mixture of product as shown in the reactions. Actually, this problem is taken from the Jerry March book, where the tosylate can give the 2 isomers, and the 2 isomers means one is that of the means to these 2 isomers can be formed by the NGP reactions. Here the methoxy lone pair on the oxygen atom is added with that of the acetate to form that of the cyclic intermediate, and then the cyclic intermediate undergoes cleavage to form that of the 2 product. Here the configuration of the A isomer and the B isomer is same. Here the stereochemistry on the stereogenic center, giving stereogenic center is same, and we get that of the A and B is the same option, that is the A, B is the correct option. Now, if we go to the Stille coupling problem, where the more substituted enolate is formed, more substituted versus less substituted enolate, in presence of the LDA, lithium diisopropyl amide is the hindered base, which can be protonated in the less hindered side to form that of the triplet derivatives, and then this triplet derivative undergoes Stille coupling in presence of the properly substituted alkene derivatives. We get that of the Stille substituted product, and this similar reaction also taken from that of the Stille coupling from the Claydon book, where the many examples are given. This is the examples where the selective dihydroxylation occurs in presence of the organocatalyst, which can selectively hydroxylation take place at the more electron rich center compared to that of the electron deficient center. Here the more electron rich center cis hydroxylation will occur at DHQD whole thalazine is the effective catalyst for that of the cis diol productions. The correct order or relative rates of the following reactions is that this is the nucleophilic radicals and this is the electrophilic radicals. We know that the nucleophilic radicals can add to that of the more effectively to the electron deficient acrylate derivatives, and hence the Kc is greater than Kd. But here this is the electrophilic radicals, so it is electron loving, so here the Ke is greater than Kd. This is the hydroboration reactions, where the hydroboration takes place in presence of the triethyl boron sodium borohydride, and the effectively we get that of the syn diol via that of the shell-like transition state, we get that of the syn product. In case of sodium trioxide borohydride, we get the opposite isomer, where the hydride ion is attacked from that of the less interface, we get that of the antiproduct. Here, the Grignard addition takes place in presence of the copper bromide, and the phenyl magnesium halide is added to that of the soft center, and to produces the soft 1,4 addition product, and the hydride minus ion is attacked to that of the top face, and the hydroxyl group is formed. Here the most stable product is formed as the where the all substituted derivatives are present in the equatorial positions. The mechanism of the following reaction involves, that is the first electrocyclic ring opening via conductory modes to give that of the formyl derivative, which undergoes disrotatory mode to give that of the pyrene derivative. So the option is that of the 4 electron conductory electrocyclic reactions and 6 electron disrotatory electrocyclic. A and C option is the correct. Now this is the problem for the heterocyclic reaction, where the acidic anhydride can add to that of the anions to give that of the acid-oxy derivatives, which undergoes isomerization and the nucleophilic addition to get that of the desired product. So the option 2 is the correct. Thank you for the watching video. Next video will come for the GATE problem solution 2024.